Good morning. Welcome back to Math 8. This is Unit 4, Lesson 10, On or Off the Line. Let's interpret the meaning of points in a coordinate plane. So the first thing we look at, which one doesn't belong? Lines in the plane. Please take a minute, pause the video, make a decision, and then let's listen to the discussion. Okay, welcome back. As I look at these, I look at letter A, and I see that that one's the only one that has parallel lines. None of those lines intersect. So I could say that A is out because of parallel lines. I could also look at item B, and I could look at that one and say, well, there's only two lines on that one, but all the other ones have three, and those two lines intersect. So B is different than the others. And then perhaps I chose C. I said, well, C is the only one that has lines that intersect all in the same spot. They all have just one common point. Whereas D has three lines that are just kind of random all over the place and not intersecting in really any common places. Maybe they intersect and make a triangle. There's several ways for us to interpret these lines. How did you interpret them? Moving on here, we have pocket full of change. So we have Jada. She told Noah that she has $2 worth of quarters and dimes in her pockets and 17 coins altogether. She asked him to guess how many of each type of coin she has. So here's a little table that shows some combinations of quarters and dimes that are worth $2. Now, I know you're probably already thinking, well, there's only one way to do that, maybe two. So what I'd like for you to do is keep an open mind and let's look for a pattern as far as what can happen as we work with these pieces. When we talk about these tables, we're supposed to complete the table. What we know is if we have $0 to make $2 or 0 quarters, we must have 20 dimes because that's what makes the $2. So any combination that we have here as an ordered pair will represent enough money to make $2, but we're looking for a specific ordered pair that will actually combine the number of coins to 17. So let's say that we have $1 in quarters, then that must mean that we have $1 in dimes, which would give us 10 dimes. That's still not 17 coins, I'm sorry. So let's keep going on. What if we have only quarters? Well, only quarters, then we would have 8 quarters and 0 dimes. Still not enough coins. So what if we have 5 dimes? That's 50 cents. So I need $1.50 in quarters. That would mean that I'd have 6 quarters. Still not enough. But what I hope that you've recognized is there's a pattern that we can look at here. All linear equations have patterns. So as we look right here, I'm just going to look at this one, 4, 8, and 6. If I wanted to bring this back into a certain order, I could start like this, and I could go 4. Actually, I want to start with the largest number. 8 and 0, 6 and 5, 4 and 10. And perhaps we can see that there's an order. For every number of quarters, for every 2 quarters I take away, I gain 5 dimes, which is that 50 cents. I don't think there's any other way to split that up any further because we can only go in increments of 10 cents. So what happens if we have 2 quarters and then 15 dimes? That would make $1.50 plus 50 cents. But here's the cool thing is we see that pair right there actually also adds up to $2, and then it has 17 coins. So what we want to look at is we actually want to look at all of these different points that can be made, can be represented on a graph. Looking right here. This is all the different ways to get $2 with quarters and dimes, at least for how it would add up. So when we look at these pieces, let's look at where each of these points would represent, or how each of these pieces would represent it. When we take a look at it, we want to look at point A. Point A represents 4 quarters and 13 dimes. Is it possible for Jada to have 4 quarters and 13 dimes? Well, let's look. 4 quarters is worth 25 cents plus 13 dimes that are worth 10 cents. And our question is, what does that equal as a total? When we look at that, 4 quarters is $1 plus 13 dimes is $1.30 for a total of $2.30, which is too much money. So we know right now this total, 4 quarters and 13 dimes, is $2.30, not $2. This is not the right combination. So we would say no. All right. How many quarters and dimes must Jada have? Explain your reasoning. Well, as we saw on the table, we know that Jada must have 2 quarters and 15 dimes, because 2 quarters at 25 cents each is 50 cents, plus 15 dimes at 10 cents a piece is $1.50, which equals $2. That's pretty good reasoning there. What you hopefully will see from this is we can actually write an equation to work for any number of quarters. We're going to see that right here with this piece, or with this expression that we started right. The expression would represent this. How many different quarters can I have? Let's say 25 cents per, let's let Q be the number of quarters, and 10 cents for every dime. And if we set that equal to $2, then we can solve for that value by simply substituting a value for the number of quarters and then figuring out the number of dimes, or vice versa. Ultimately, what it comes into is a game of guess and check. One other way that we were talking about is looking at this graph here. What we could talk about is I could have all the different ways that I could make 17 coins. Now, this doesn't necessarily equal to $2 at all. There's just one sweet spot where we get 17 coins and $2. So when we talk about 17 coins, she could have 0 quarters and all dimes, but that doesn't give us $2, or 1 quarter and 16 dimes, or 2 quarters and 15 dimes. That one is that good spot. As we saw right here with point A, what does point A mean? That's 8 and 9. We're going to go back to this. What does it actually mean? What does it represent? That's 8 quarters and 9 dimes. And then how much money in dollars is the combination represented worth? So we have 8 quarters at 25 cents a piece, plus 9 dimes at 10 cents a piece. And we're asking what's the total for this. We know 8 quarters is $2, and we know 9 dimes is 90 cents. So our total, what it represents, is $2.90. So we know that this, while it is 17 coins, it's still not our $2 mark. Just the same as what we saw with 4 quarters and 13 dimes, not our $2 mark. But we know that she has to have, according to the graph, 2 quarters, 15 dimes. That's the only spot that will actually make this situation true. Looking at our next one, Claire and Andre are making signs for all of the lockers as part of the decorations for the upcoming Spirit Week. Yesterday, Andre made 15 signs and Claire made 5 signs. Today, they need to make more signs. Each person's progress today is shown in the coordinate plane. So we have one line that represents one person and one line that represents the other person. What we know about this is that this line down here on the bottom must be Claire, because she started with 5 signs. And we know that Andre, he started out with 15 signs. So this is, of course, the next day. This doesn't include the signs, or doesn't talk about the previous day. So this is today, starting right here. And so we need to answer some questions here. I want to go ahead and graph these, or mark these lines. This is Claire, and this is Andre. So based on the lines, mark the statements as true or false for each person. At 40 minutes, I have 25 signs completed. So this is speaking as if you're Claire and Andre. So we come over here to 40 minutes, and then we go up to 25 signs. And they said, I have 25 signs completed. Well, that's true for both of them. I see that both lines are intersecting that single point. So we would say true and true. Let's talk about this one. At 75 minutes, I have 42 and a half signs completed. So we come over here at 75 minutes, and we come up here. There's 10, 20, 30, 40. This is 45, so 42 and a half signs. This one is true for Claire. but this is false for Andre because he doesn't have that many signs done. At 0 minutes, I have 15 signs completed. As we see over here, 0:15. That one has to be true for Andre, but not for Claire because she didn't have that many signs done. At 0 minutes, I have 60 signs completed. Looking right here, 0, and then we come up to our line of 60. So 0 and 60, point D. And we notice that point D is on neither line, so that tells us that both of these are false. So interpreting the graph, we can see that as a linear equation, we can see that they're making a certain number of signs every single minute. We can see that Claire, while she started out with fewer signs, she really got into gear the next day and she made a lot more signs, a lot faster than Andre did. So we could ask ourselves a couple of questions. Which is a true statement for Claire and Andre, or what is a true statement for Claire and Andre at 20 minutes? Well, we could say at 20 minutes, Claire had made 15 signs, and at 20 minutes, Andre had made 20 signs. So all we're really looking for is looking for that information that's on the graph. What do we know about the point 20 and 15? Well, if we look at 20 and 15, what do we know about that point is that Claire had made 15 signs after 20 minutes, or in 20 minutes, Claire made 15 signs. And what we know about Andre is in 20 minutes, he made 20 signs. This would be true anytime we go all the way through. And what we know about points like if we chose this one, 40 and 25, such as what we saw down here in the table, what we could say is at 40 minutes, both people had made 25 signs. And what this would be is when we compare these two equations in the same plane, we call that a system of equations. And that system of equations is being satisfied or is being made true by one single point. And that one point is the one solution that those two equations share in common, meaning that this is the one and only time that the equation for Claire and the equation for Andre can be equal to each other. That's the direction we're heading with what we're doing currently. That's where we're heading with this. So don't stress too much if you don't understand that just yet. All right, the last thing is ready for more. This is a little bit of a challenge question to think about how I could make an equation that represents a bunch of a pattern in the toothpicks. What we see is we have 4 toothpicks makes up 1 square, and then 7 toothpicks makes up 2 squares, and then 10 toothpicks make up 3 squares. So then the question is, hopefully what you've already seen there is a pattern developing that in 1 square we have 4 toothpicks, 2 squares, 7 toothpicks, 3 squares, 10 toothpicks. We see that we're increasing at a rate of 3 toothpicks every single square. But 3 toothpicks doesn't make a complete square. So what's actually happening here? If we take these toothpicks, that's 4, so we take 4 of them, and then we add 3 more. We take 4 and add 3, add 3. How could I recognize or represent that? What if you actually looked at it as saying 3 toothpicks plus 1, 3 toothpicks, 3 toothpicks plus 1, 3 toothpicks, 3 toothpicks, 3 toothpicks plus 1. So in here, what we can actually say is in figure 1, we have 3 toothpicks plus 1. In figure 2, I'm actually going to put numbers. In figure 2, we have 3 toothpicks. I shouldn't put parentheses yet. Or 3 toothpicks for 2 squares plus 1. And we see that right here, 3 toothpicks plus 3 toothpicks plus 1. And right here, we see that pattern going on as well. So 3 times 3 plus 1. And we recognize that we actually have the correct quantity each time. There are 4 toothpicks here. This is 6 plus 1 is 7. 9 plus 1 is 10. We're all correct. So how would I represent that pattern? We would see 3 toothpicks per square is the constant that keeps happening. That's over and over and over. And then to complete the total of the squares, we have to add just 1 more. So if we want to have 10 squares, we need to think about this as saying the expression 3 times 10 squares, or 3 toothpicks for 10 squares, plus 1 is going to give us 31 toothpicks for this situation when I look at 10 of them. All right, So what we've done here is we've studied linear equations in an earlier unit. We've learned that the values of x and y must make an equation true, or that make an equation true correspond to the points x and y on the graph, talking about any point on here. When we talk about x and y would make that true. Also talking about the coins. When we talked about, like 4 quarters and 13 dimes would make this expression true and tell us how much total money we have. And then we see that as an example right here. If we have X pounds of flour, it's 80 cents a pound, and sugar for 50 cents a pound. And we're looking at a total of $9 that we can spend. Then we can write out the equation to figure out how many pounds of each one we got. So we talk about 80 cents for a pound of flour, 50 cents for a pound of sugar, and then we can just break these down. We can make a table is one way to do this. It's probably one of the easiest way to do this, or we can graph the line and then we can see all the points like we did in the coins. Here's an example of that graph. And then we can kind of catch on to the whole fact that there's only certain solutions that will make this line true. Like we look at points 1 and 14, that is $15 when we talk about $1 for total for flour, or excuse me, 1 pound of flour plus 14 pounds of sugar is 15 pounds, but it's not the right amount of money. We talked about adding 5 pounds of flour and 10 pounds of sugar, and that does add up to the right amount of money of $9. But when we see we come over here, 9 pounds of flour, 16 pounds of sugar, that's not going to add up to the $9. It'll actually add up to $15.20. So we need to understand a couple of different pieces. Talking about, well, how much weight do we have also helps us to narrow this down. If we knew that the flour and the sugar together would 15 pounds, that would help us to draw another line and another conclusion about how much flour we have. And that would be this piece at 15 pounds. We could either have all sugar or we could have all flour. We could draw that line. We see that the two lines intersect. They make both equations true at the same time. The coordinates of a point on only one line makes only one equation true. And if the coordinates right out here, like this one, 916, is on neither line, then it doesn't make either of them true. Again, over here, this does make it true for the amount of flour and sugar we have, but not for the amount of money we have. This is the only spot where the amount of flour and sugar equals the $9. So that's what we're putting together today. We are going to continue to get better at this one. Hopefully this is a good start for you. We'll see you in the homework.